All right, good morning, everyone here and hopefully online. It's my pleasure to introduce Professor Simon Doclo from the University of Oldenburg in Germany, who's going to talk about multi-microphone speech enhancement. And with that, Simon.
Okay, thanks a lot, Hannes, and thanks for people showing up for this unannounced talk. So as you mentioned, the topic will be on multi-microphone speech enhancement algorithms, so noise reduction and dereverberation algorithms. And as I don't have to tell anybody here, in many typical acoustical environments, there ambient noise and reverberation is present, which actually degrades the speech quality and intelligibility for speech communication applications, and also reduces the performance of ASR systems. And I will be mainly talking about speech communication applications, such as, for example, mobile telephony, or also other applications which are quite in my interest field, which are hearing aids and hearables, where you have the same kind of problems degrading speech quality and intelligibility. Of course, there's also other applications without making publicity for any specific device. Just going to plug this in here. Of course, also smart speakers are of interest there, where also these problems occur. And as already mentioned, I will mainly talk about speech communication applications where latency aspects are quite important. So this call then also for online processing algorithms, which also need to be blind in most applications where you don't know exactly where the microphones are located. Also something that will pop up regularly in the talk is that they need to be able to work for time varying, could be even highly time varying dynamic acoustic scenarios with moving sources. And in this talk, I will not focus on DNN-based algorithms, but more on traditional signal processing algorithms. Not that I don't believe in these algorithms, but of course, I just want to focus on more traditional algorithms that exploit the knowledge and statistical models of the speech signals and the room acoustics. So, more in particular, what will I talk about? First of all, I will talk about the joint estimation of time-varying spatial and spectral variables, more in particular the relative transfer function of a moving speaker, as well as the PSDs of noise and reverberation. In the second part of the talk, I will focus a bit more on hearing devices, and more in particular binaural hearing devices at two ears, where the aim is not only to do speech enhancement, to reduce noise and reverberation, but also to preserve the complete auditory scene, so the spatial impression of the auditory scene. And then in the last part, I will also extend these hearing devices, or in general, microphone arrays, to acoustic sensor networks with spatially distributed microphones. Okay, let's just get started on joint reverberation and noise reduction algorithms. So this is the signal model where we just assume for now a single speech source in a noisy and reverberant microphone and microphones where we don't know where these microphones are located. In the short-time Fourier transform domain, the noisy and reverberant microphone signal, empt microphone signal, at frequency k and time frame L can be also written as a convolution of the convolutive transfer function with a clean speech at this time frame and frequency plus noise. Can be different kind of noise, sensor noise, diffuse background noise, can also be an interfering speaker. We can also actually use this model directly, but in some other models, we split it into, let's say, the direct and early reverberation present in the current frame, plus all other terms, which are then late reverberation, and of course, still this ambient noise term. If we stack everything into one vector for all the microphones, then this vector, m-dimensional vector y, can be written as A, which is just a vector, times this x1, the signal you would actually like to estimate, plus late reverberation and noise. And this vector A is called the vector of relative early transfer functions in a reverberant environment. If you would not be familiar with this kind of terminology, in an anechoic environment, you can just think of it like a steering vector, which is determined by the DOA, by the direction of arrival of the target speaker. But in a reverberant environment, you also take into account some early reflections in this steering vector, or in this vector A at least. Now, depending on the model we take, actually, this one or that one, there's different kind of algorithms that are can be derived and that are quite common to use for joint dereverberation and noise reduction. If we start with the steering vector model, let's call it this way, then we can actually derive, let's say, very traditional algorithms like beamforming and spectral post-filter, where first all the microphone signals are combined with a beamformer, and then a spectrotemporal post-filter is applied to the output of this beamformer. And there actually, it's, I think, important to realize that at the output, so for the spectral post-filter, each time frequency bin is multiplied typically with a real valued gain. Another kind of approach, which directly starts from this convolutive transfer function model, takes another approach where we don't multiply each time frequency bin with a real valued gain, but we aim at subtracting a complex valued estimate of the late reverberation and the noise. And therefore directly also taking into account the phase of the signals. So I will actually explain some advances in both of these classes of techniques in the first part of this talk. Things we did in Oldenburg, but also, of course, other people have worked on this kind of approaches. So, in the first approach, beamforming a spectral post-filter, there's actually a kind of workhorse algorithm, I would call, is the parametric multi-channel Wiener filter. And the idea for people who are not familiar with this multi-channel Wiener filter is basically to estimate the desired speech component in a reference microphone signal, which for now is not yet important, which one to take, plus also to trade off speech distortion in one term and noise reduction in another term with this parameter mu, which actually trades off both desired objectives. The solution of this minimization problem can be written in terms of this correlation matrices phi x and phi n, which denote actually the speech and the noise correlation matrix, and they could, in principle, be estimated based on speech presence probability. However, since quite some decades, it's also known that this multi-channel Wiener filter can be decomposed as just an NVDR beamformer, doing actually the spatial filtering, and then a spectral post-filter. That's all well known. The question for, let's say, everybody still working in this field is how to estimate all these quantities. If they can be estimated in a very accurate way, you get actually a good performance in terms of noise reduction and also reverberation. So this was just, let's say, in general, multi-channel Wiener filter, also split in NVDR beamformer and spectral post-filter. If you now specifically plug in this model with steering vector, late reverberation, and noise, and we assume that all components are independent of each other, which is not completely true, but it's typically done. It's also not that bad. Yeah? And also, in addition, we assume that late reverberation can be modeled as a diffuse sound field, which is also not completely accurate, but it's also typically not a bad assumption. That means that this correlation matrix for the late reverberation can be written as a time-varying PSD of the late reverberation times a coherence matrix, where we assume diffuse noise for this coherence matrix gamma. If you then plug in everything in this multi-channel Wiener filter, we get basically the same expression as before, where now we just have this phi d and gamma as additional terms. So, again, it's a bit of a recap, but what are the key estimation tasks there? We need to estimate this vector A, which is this relative early transfer function vector. You can just do this very easily. Anechoic, just estimate the DOA, and then you need also the microphone configuration, or at least a model, for example, to estimate or to determine the relative transfer function vector from this DOA estimate, or you can just estimate it in a reverberant way, which I will also do and propose. Secondly, we have this time-varying diffuse and late reverberant PSD. You could also have different models. You can have a single channel model, for example, with an exponential decay. That's just a temporal model. Or it could be based on this multi-channel diffuse sound field model. And then last, we also need an estimate of this noise covariance matrix. What I didn't stress, but I mentioned in the beginning of the talk, is that all of these variables or parameters, they're time variant, they're time varying. So we also, in all of them, just in the notation, there's still an L. This frame index is still there. They can vary over time. We can have, of course, moving sources. Obviously, the diffuse sound field is still time varying, at least the PSD is time varying. And also for the noise covariance matrix, in principle, it can definitely be time varying. In the next slides, I will discuss some methods for estimating this RTF vector and this PSD, either in a, let's say, separate way, or in a joint estimation way. Just for the notation here, there's a bit of formulas here in the beginning of the talk, but I think that's fine. All the variables in red, these are the variables we will estimate. So you could say the unknowns. And the blue variables are some assumptions. For example, this diffuse sound field model. First, there have been quite some methods which aim at estimating all the PSDs, so of the late reverberation, the noise, and the speech, which assume that an estimate of this RTF vector is actually available. And also, sometimes that even the noise covariance matrix is available, maybe estimated in the beginning of the segment of the signal. If you then have an estimate of the reverberant speech PSD, can be written based on this model with the PSDs, the RTF vector assumed to be known, and the late reverberant PSD. And as I mentioned, there have been many, many estimators in the last couple of years, either maximum likelihood estimators or even easier, closed form least squares estimators based on minimizing the Frobenius norm between this matrix and this model. In last year, we actually published a paper with several groups where the aim was basically to compare all of these estimators, and the conclusion was maybe a little bit disappointing. But you could also say in a positive way, they all worked quite well, but they all worked very similar. So if you're interested in these estimators to learn more about it, I would say in this paper there's quite a nice overview, just also giving the relationship between these different estimators. But all these estimators assumed that the RTF vector of the target speaker was available or known. So what you actually would like to do, I think, is estimate everything in a joint way. So joint estimation of this time-varying RTF vector of the speaker and also all the PSDs. In one method, which requires the estimate of the noise covariance matrix, so basically we have the same kind of equations, but now also this vector A is now in red. We also would like to estimate it from this model. A state-of-the-art method for doing this is called covariance whitening method. So basically it pre-whitens this estimate of the reverberant speech covariance matrix. You can get a nice model with a rank 1 matrix and an identity matrix. And then based on the eigenvalue decomposition of this pre-whitened matrix, I will not go into details here, the eigenvector is related to an estimate of the RTF vector, and the eigenvalues are related to the PSD estimates. Another method which we recently proposed at ICASP this year, I would say not goes back one step, but doesn't need an estimate of this noise covariance matrix, models it also, and tries to minimize this Frobenius norm, but now estimating both the RTFs A and all the PSDs for the speech, for the early speech, the diffuse part, and the noise. Unfortunately, there's no closed form expression anymore for minimizing this Frobenius norm with respect to all of these variables. So what we proposed there was an iterative procedure, two-step iterative procedure where actually it can be shown that for the PSDs, it's a very easy least squares problem, and for the RTF vector, it's again an eigenvalue problem. And then by iterating it a couple of times, actually not so many times, we typically just do this 2 or 3 times, you can actually have a quite good estimate of both the PSDs as well as the relative transfer function vectors. Okay, these equations are not that important, it's just in the paper. Okay, let's listen to some sound examples for this first class of methods. I would say really rather traditional, just beamforming plus post filter, where we estimate all of the quantities, so spatial as well as spectral post filter. So we have some simulation results both for a simulated stationary source with a room impulse response from the ACE challenge database with a reverberation time of about 1.2 seconds. And also in our lab in Oldenburg, where we can change the reverberation time with these absorption panels, we have just recorded a moving source, but actually different moving sources, with another microphone with 6 microphones at 1 centimeter interspacing, and also generated some pseudo-diffuse babble noise by just playing back some noise at the loudspeakers in the corners. All typical simulation parameters, 16 kilohertz, rather short STFT in order to have a limited latency, And then also the typical assumed parameters for these iterative methods or for the covariance whitening method, where most of the smoothing is actually quite short in order to be able to track moving sources. So let's listen to some sound examples. First for the simulated stationary source. This was the input.
In the course of a December tour in Yorkshire, I rode for a long distance in one of the pumps.
Okay, and then just at the output of this alternating least squares algorithm.
In the course of a December tour in Yorkshire, I rode for a long distance in one of the pumps.
So it does some dereverberation, some noise reduction. There are some artifacts of musical noise. You can get rid of it by some tuning and some post-filtering. But that's basically what can be achieved by estimating everything jointly. Also for maybe the recording moving source. Now I realized when preparing this talk, it's actually in German, but there was a German speaker then moving around in the lab. Yeah. Oh.
Peter gibt 2 schöne Messer. Kerstin schenkt 3 schwere Blumen. Kerstin.
So this was a speaker moving from 0 to 90 degrees apparently, and then after processing.
Peter gibt 2 schöne Messer. Kerstin schenkt 3 schwere Blumen. Kerstin.
So this does some dereverberation, some noise reduction, but I would say in this class of techniques, that's more or less what you can achieve just by doing beamforming and spectral post-filtering. So let's move to the second class of technique, which takes a different approach, where we aim at subtracting a complex valued estimate of both the late reverberation and the noise. And so basically it starts not from this steering vector model, it starts really from this convolutive transfer function model with h of m, the convolutive transfer function in each frequency bin, plus the noise. And it will aim at estimating S using statistical models of both the speech as well as of the reverberation, or at least the room acoustic propagation in the room. What can also be shown, as we show later on, is that it will exploit sparsity properties of speech in the STFT domain. That means actually we all know that clean speech compared to reverberant speech, that clean speech is sparser in the time frequency domain than reverberant speech, or said in a different way, reverberation will lead to some kind of smearing in the STFT domain. What it basically does is reformulate this convolution in a so-called autoregressive model, where it can be shown that the reverberant speech component in the reference microphone here, without laws of generality, the first one, is equal to the clean signal, including early reflections, plus a filtered version of delayed microphone signals, where this delay actually plays quite an important role in order not to later pre-whiten the signal. These terms G, these are the prediction filters with a certain length that depends also on the reverberation time. But this is just a mathematical model. That means we can completely reformulate this one into this model. That means we can also estimate now D, our clean speech signal, by filtering the signals and then subtracting it from the reverberant signal. So that's basically done here, or just in a block diagram. We have our reverberant microphone signals, can also be noisy. We delay them, we have some filters, then we subtract this estimate of the late reverberation from the reverberant signal. The only question is, of course, how do we compute these filters G? Theoretically, we know it's possible to completely dereverberate. Now we just need to compute or determine these filter coefficients, these prediction filters. Already in 2010, there was a nice technique by NTT from Tomohiro Nakatani called multi-channel linear prediction or weighted prediction error, whatever term you like most, which assumed that a time-varying Gaussian model actually for these STFT coefficients. We took that approach and also extended it a bit to a more general prior. So we assumed it's not a time-varying Gaussian model, but it's actually time-varying super Gaussian or sparse prior. This sparse prior for each time frequency coefficient can be written as a maximization over Gaussians, where this scaled Gaussian, where the scaling function can be interpreted as a hyper prior on the variance. By then plugging this into a maximum likelihood cost function, assuming actually also all the frequency bins are independent of each other, minimizing this, basically, this is the minimization problem that needs to be solved. Without further ado, that's where you can just read the paper. It can be shown this can be solved by an alternating optimization problem again, where in one step these variances are assumed to be fixed and you estimate these prediction filters, and in the next step you assume this prediction filter is fixed and you estimate the variances. There is still this, I wouldn't say nasty, but still a nasty function here, this hyperprior, and there you can take in different approaches. What we did to make it a little bit more practical is assume a complex generalized Gaussian prior with just one parameter, a shape parameter p. And this can be seen as follows: that for yeah, sure.
The idea behind using sparse Gaussian terms?
Because we wanted to also control, that actually can be seen later, the sparsity in the time frequency plane. So we wanted to have some control parameter there for the sparse prior. Secondly, it's also known that actually speech is not perfectly modeled by a Gaussian model, but it's actually more super Gaussian. So that was the main motivation behind doing this. So if we then plug in this complex generalized Gaussian, we can actually play around a little bit and go either from a Gaussian model where p is 2 to this one, to a more sparse prior, more peaky prior, you could even say, for a smaller value of p. Yeah, so that's just an additional control parameter which is there to control this sparsity. It turns out, and that was also a nice thing, which of course we didn't know in advance, that if you plug in this CGG prior, that basically for this estimate of the variance, it was just the estimate of the desired signal in some iteration to the power 2 minus p. Where in the original approach p was just 0, so it was just to the power 2, and in our approach it's 2 to the power minus p, which is a very easy, I would say, generalization of this original approach. What we also found out is that this kind of approach can be interpreted, it's equivalent to minimizing the LP norm over each frequency band, so over time, so the LP norm of these coefficients. So basically, you introduce or you promote sparsity depending on the value of p over these time frequency coefficients across time, especially for small values of p. So that gives you some, I would say, degree of freedom, some extra parameter to control or at least promote this sparsity.
So would you set p to be the same value across?
Yeah. So what we did in this original work, it's already 2015 that we did this. It was just a fixed value. So we just tried fixed values also over frequency, which definitely is not the optimal, but that's how we started. And I also noticed that actually last week at WASPA there was a paper from another group where they aimed actually at optimizing p depending either on speech quality or also automatic speech recognition performance. But it was also really put in a neural network-based architecture to optimize this p-value. I even think even better would be if you can control p over time, but that depends a bit how this, or it needs to be seen how this can be done. Yeah. So in our original approach, we just took a fixed p just to check what really happens. Yeah.
Is there like, if you look at clean speech, is there a particular frequency dependence that you observe for this p?
Yeah, no, I would say it depends on the speech. So it's not, in general, I would say the higher frequency, it's more sparse. But even more important, that it should depend, I think, on the real speech signal or on the actual speech signal that is there to actually optimize this p-value, which is not that easy in a sense to do. Yeah, but, good. Also, there's some additional work which is maybe not that important. You can also incorporate some additional knowledge. You can have multiple outputs, which is important when you also talk about joint dereverberation and noise reduction. And there's also recursive versions, so adaptive versions available for moving sources. Basically, here I will just play, let's say, the first and simplest version where we just have the batch implementation, without noise, but if people are interested, of course, I also have different files available there. So just to see what this approach can do in terms of dereverberation, I'll play the clean signal, then the microphone signal, the reverberation time of 700 milliseconds, 4 microphones, typical STFT parameters, and then the output signal.
They are rated single A1 by Moody's and single A+ by S&P.
And the microphone signal.
They are rated single A1 by Moody's and single A+ by S&P.
And then the complete process signal.
They are rated single A1 by Moody's and single A+ by S&P.
Even if it's played in a reverberant room, I think you can definitely hear the differences. Okay, so what are still challenges or current and future work? In the first part of the talk, I talked about this joint estimation of RTF vectors and PSDs, but this was just for a single source scenario. Basically, there's typically multiple sources, multiple moving sources. So we would like to estimate all the RTF vectors and all the PSDs. And I would say typical approaches can only estimate the subspace of these RTF vectors, and you would like to have the separate ones. So we're working on also the separate estimation for multi-speaker scenarios in a paper that's currently in review. And for this more subtraction problem, where you subtract a complex valued estimate, I only talked actually about the dereverberation, but of course you would like to have joint dereverberation and noise reduction. There we actually, in conference and also in a journal paper, we proposed some scheme that actually combines this MCLP, or weighted prediction error, together with generalized side lobe cancellor for the noise reduction. Well, you cannot split it really between generalized side lobe cancellor for noise and the other one for dereverberation. They really work in a joint way. So that's what we're currently doing in this area. Okay, let's move to the second part of the talk, binaural hearing devices. So there, as I already mentioned, the aim is not only to reduce noise and reverberation, but also to preserve the auditory impression of the complete acoustical scene. And actually, these hearing devices, of course, they generally have multiple microphones available. If you have a monaural device, it's like 2 or 3 microphones. If you move to binaural devices, you have, of course, more microphones available at both ears. And you can also think about extending this and using hearing aids together with external microphones, which are depicted here by these extra microphones. And as you can see from this picture, this work didn't start yesterday, but a couple of years ago, when there were still these kind of old-fashioned mobile phones available. So if you want to preserve the spatial awareness of the user, or preserve the auditory impression of the acoustical scene, this can basically be done by preserving, or at least aiming at preserving, the binaural cues of all the sound sources in the acoustical scene. And what are these binaural cues? I probably don't have to tell people here, but still, just as a recap, for a localized source, for example, this source, this is a person, there's the ITD and ILD cues, so the time difference and also the level difference because of the head shadowing effect. But also, and that's maybe not clear for everybody, is that there's also the interoral coherence cue, which is especially important in reverberant environments or for non-localized sound sources, like in the extreme case, a diffuse sound field. And this interoral coherence describes the spatial characteristics, for example, the perceived width of such noise fields, and actually also determines when these ILD and ITD cues are reliable, for example, in reverberant environments. So this is actually the configuration we're considering here. We have a hearing device on the left, hearing device on the right, each having some microphones, multiple microphones. For this part, we assume that all microphone signals are available at both devices, so kind of a perfect wireless link, or a wire, or a device which is just connected over the head. And the main difference about this, let's say, binaural algorithms, as I would say, is it's not that they're maybe having devices at both ears, but they're also generating 2 output signals. And that's actually the main difference, I would say, to monaural or algorithms. So we have 2 filters here, W1, W sub 1, W sub 0, generating two output signals where we want to reduce noise, reduce reverberation, but also preserve the auditory impression of the complete scene. I mean, that's at least the goal we're aiming at. In my view, there's actually two main paradigms for achieving such goals. On the one hand, there's so-called spectral post-filtering, where basically one microphone, reference microphone, is taken on the left and the right side, and it's basically filtered by the same gain. If it's filtered by the same gain, then actually you will not change the ILD cues, and typically also you will not change too much the ITD cues of these sources, of all sources. This gain can then be computed in any way you like, single microphone case, or first applying the best spatial filter you can think of, even not maybe caring too much here about speech quality, and then deriving the gain from that filter. On the other hand, there's, I would say, true spatial filtering techniques, which basically take all microphones from all sides and design two different spatial filters. We've been mainly working on this second paradigm, because it is, well, true spatial filtering. You can also, of course, integrate spectral post-filtering on top of it afterwards. But as I will show, by just using these two spatial filters, for example, MVDR or multi-channel Wiener filter, it cannot be guaranteed that the binaural cues of all the sources are preserved. So here I will not go into detail into the formulas. These are just basically the binaural extensions of the MVDR beamformer and the multi-channel Wiener filter, as I explained before. But now there's two optimization problems for both sides, both for the MVDR as well as for the multi-channel Wiener filter. The only thing I would maybe like to stress here is that what they basically do is estimate the speech component and the reference microphone at both ears. So just by design, actually, they aim at preserving, at least for the target source, the binaural cues, or at least the cues present in these microphones. So what you don't have to do here is, for example, estimate the signal and then reimpose cues or respatialize the cues on the enhanced signals. I think that this approach is actually more appropriate because for different users, these cues are already here at these microphones. So you don't have to take care of different users about different microphone configurations. Hello, Ivan. So
I increased 50% the attendance here.
So basically, what I will also show, and what most people would think, these things have a good noise reduction performance, but what about the binaural cues of these binaural algorithms? Let's just look at this example here. We have a typical example, hearing device user, binaural devices, speech source coming from the front, and some diffuse background noise. If I now apply this binaural NVDR beamformer or multi-channel Wiener filter, what happens? Basically, the noise is reduced. Good. But it will now be perceived as coming from the same direction as the target speaker. So that's really undesired or even dangerous in some applications, like in a traffic situation where there is a car passing by that, well, if you hear the car coming from the same direction as the speaker, that's definitely not a good idea. So that's a problem, and in the past couple of years, we've actually come up with different approaches for not doing only noise reduction, but also preserving then the auditory impression of this complete acoustic scene. So on the one hand, we've extended this, since we wanted to preserve, for example, for diffuse noise or diffuse noise-like environment, the interoral coherence. We've added some extra terms to this cost function. Here, this is really the coherence of the output, and we wanted to have it as close as possible to some desired coherence. This looks a bit like a complicated cost function. It's also complicated. It was good for a paper, but maybe not to implement in practice. On the other hand, we've proposed a technique called partial noise estimation, where basically in this multi-channel Wiener filter, we don't aim at completely reducing the noise, but the goal is actually to only estimate a scaled version of the noise components in the microphone signals. And the nice thing, and that's maybe not directly visible from this equation, is that it just turns out that it corresponds or relates to mixing the output of this binaural NVDR beamformer or multi-channel Wiener filter with part of the noisy input signals. So this is just, let's say, the NVDR beamformer with RTFs implemented on the left and the right device. And then you just scale it with some factor and mix it again with some noisy input microphone signals. Of course, depending on eta, then you will get some loss of your noise reduction performance. But what you hope for is that by preserving also the coherence of the diffuse noise, that, at least for normal hearing people, binaural unmasking will actually make sure that you don't lose too much of speech intelligibility, or you even gain speech intelligibility. So, how can we choose now this trade-off parameter? And there's actually different ways. If you are striving for a very easy solution, no computational complexity, you just take a broadband value. Something between 0.1, 0.3 actually works quite okay. In the last years, we've also come up with some better approaches, which are more psychoacoustically motivated. And we've looked at the approaches which depend or are based on the discrimination ability of the human auditory system for this interoral coherence. And there are several psychoacoustic studies that have shown that if the IC is high, then you shouldn't touch it too much because then you will actually hear it. However, if the interoral coherence is low, then you can mess it up a bit and most people will actually not perceive it. And, well, of course, you shouldn't completely mess it up, but up to some value you can actually change it. For this specific example, if you look at the binaural interoral coherence, that's this black line. It's actually the magnitude squared coherence. It's like a sinc squared function. Yeah, so for the low frequencies, it's, let's say, relatively high. So there we try to really preserve it. For the higher frequencies, we can change it a bit, and most people will probably not perceive this. So in all these approaches, then we set just the desired MSC level, and we compute this mixing parameter based on this, or aiming at achieving this desired magnitude squared coherence. Yeah.
Sorry, but
yes.
This doesn't say anything about the trade-off between the binaural unmasking and the loss in noise reduction, right?
No. So there the aim is just we want to preserve as well as possible the auditory impression of this diffuse noise. Yeah. So of course you could go further and say, no, I don't really care too much there, and I want to have maximum, let's say, noise reduction. Yeah. So it doesn't say anything about this trade-off. That's completely true. I think also in order to really bring in this trade-off, you would also need to know for specific persons almost how well they can use their binaural cues. Because I'm also thinking about not only normal hearing, but also hearing impaired. And there we saw that for normal hearing, there you could maybe say most people are similar in their binaural cue exploitation or usage. But for hearing impaired, it's quite different actually. Some people cannot use it, and then I will just go for maximum noise reduction, not caring about spatial perception. For normal hearing, I would say it's still more important. But you're completely right, it doesn't bring in this kind of trade-off in this way. Yeah. Which could be done. We also have another approach. I will not go into more detail. We're changing this eta parameter, so this mixing parameter, in a time frequency dependent way. So we're even changing this over time, where the main idea still is, or in a very intuitive way, if you have if you don't have a lot of noise reduction, it's actually more important to preserve the binaural cues, because you anyway didn't do a lot of noise reduction. If you have a lot of...
What is on the horizontal axis from 0 to 1?
It's this mixing parameter. And here is the MSC, so the coherence actually between the input signal and the output signal. You can show that it actually corresponds. That's why I put also SNR. That's easier to understand. If you have in your beamformer or whatever algorithm you have a high SNR increase, so we have a lot of noise reduction. Actually, it's more important to keep that noise reduction than to preserve the cues, and the other way around. That was the main motivation for mixing a lot when there is almost no noise reduction, and not mixing too much for this. I mean, this curve you can optimize in different ways. I mean, this was just
So technically, this is a curve which tells how much noise you suppress based on how high is it.
No. So this is actually, here you say actually how much did I suppress the noise. That's basically what it says. I mean, you have to estimate it also. You could estimate also the SNR improvement, but we noticed it's actually a bit easier just to compute the coherence between these two signals. So here you could also just say, I estimate how much noise I suppressed. There's different ways for doing this, right? Yeah.
But high coherence means that the output of your spatial filter and the original signal is pretty much the same.
Yes.
Which means you have a low signal to noise ratio.
Mm-hmm.
And then you literally throttle your noise suppressor so you don't introduce the artifacts. by putting eta at max.
Eta at max is actually just taking the input signal almost.
Yep.
Done.
Very nice.
Exactly. Yeah. Well, we were not the first proposing this actually. I can also say, but what we propose is not using an SNR estimator here, but just using this coherence. That's all. Yeah. Okay. So let's look at some psychoacoustic data or some subjective listening experiments. It's for a simulated environment. So binaural recordings. There was a Kemar here, 2 hearing aids, a source from minus 35 degrees, realistic ambient noise, some people in that cafeteria. And we have just binaural NVDR beamformer, and then different mixing schemes. Without going into too much detail actually here, how we got to these specific parameters. 11 normal hearing subjects, and we measured both spatial quality, so how much the output sounds like the input, I would almost say, using a Mishra-like paradigm, and speech intelligibility with a speech reception threshold in a matrix sentence test. In German, since we're German subjects, but I don't think that the language is important here in these aspects. And the main question we wanted to ask is, okay, technically we have an SNR decrease because we mix. You cannot actually change this. But does actually binaural masking of the human auditory system then still compensate for this technical SNR decrease? So let's first look at the spatial quality. And there we just ask the subjects, just rate the spatial difference between the reference input signals and these output signals. They were not, let's say, highly trained subjects, but at least they were students, and so they know if you just say rate spatial difference, what is meant. And you can first see, okay, the hidden reference is most of the times correctly identified. It's already good in the Mishra test. Binaural NVDR, everything is coming from one direction, so it's really poor. And then these mixing schemes, depending on which scheme we take, we get a better performance definitely than binaural NVDR, and it even seems that for one of these schemes, it's almost as close as the input signal, so the rating. So that's good. At least mixing preserves or improves this spatial quality. Of course, the question is then what happens to the speech intelligibility? I should remind everybody here again that for normal hearing subjects, so at the input, the SRT was about minus 7 dB, which is a typical value for diffuse noise. The NVDR with these 4 microphones brings about 4 dB improvement. That's also according to literature, but it can be expected. And all our mixing schemes are pretty much the same. So there's no statistically significant difference in the SRT between all of these schemes. So basically what we did is we didn't change the SRT. Okay, happens. I mean, could even have improved theoretically, but it didn't change the SRT while still improving very much the spatial quality of this scheme. It's always a bit hard to play back binaural algorithms in a room, but I will still just play back something just to give you some impression about the kind of noise reduction that can be achieved. Yeah. So this would be the input signal. So this more or less the same scenario. Now the speaker is at minus 45 degrees, 0 dB input SNR, and pretty much the same kind of algorithms.
A boy fell from the window.
Then just spatial filtering.
A boy fell from the window.
With some spectral filtering.
A boy fell from the window.
What you cannot hear here now, but you just have to believe me, everything will come from the same direction. And then if you mix in things, and I will play back input, then just MWF, so multi-channel Wiener filter, and then by mixed in with the NVDR, NP scheme. So this is input again.
A boy fell from the window.
Just binaural MBF.
A boy fell from the window.
And then with mixing.
A boy fell from the window.
I pretty much heard the same kind of noise reduction, but of course you should experience this with headphones. Of course, everybody's happy to do this later on. They can also share the files. Okay, and then in the last 5 to 10 minutes, I want to talk about extending these binaural devices with external microphones, so remote microphones. Again, it's not the first time we've been doing this. There's been some other work also in hearing devices with remote microphones. Also, most of the hearing aid companies have some kind of remote microphone, which they typically just stream to the hearing aid user, losing hence all binaural cues. And so what we've done in the last years is come up with some very low complexity scheme to estimate and track this relative transfer function of the target speaker, so also for tracking this moving source scenario. And you can also show, but I will not discuss this here in this talk, that by adding this external microphone, you can basically both increase the noise reduction as well as have a better binaural cue preservation performance, which may be not unlogical. You have some additional information, but we had some theoretical results on how much it improves both cases. So I will just discuss, let's say, this low complexity method to estimate this relative transfer function, AL and AR, for both devices using the scheme.
Relative transfer function is between what? I have a microphone here which can be like this, like this, like this.
No, it's important to notice. So we have like a microphone array. It's unimportant where they are. On the device, somewhere spread out. And the relative transfer function is this complete vector of all the microphones compared to a reference on the left and a reference on the right.
Oh, okay, I see.
And why do we do this? Is because then we will definitely also preserve the cues of the target speaker. In these microphones, they're here.
Yep.
So why don't you use them? I mean, I mentioned this a bit before, but what we don't want to do, which some other people propagate, is say, okay, we estimate the signal and then we respatialize. I think it's okay, but we take more the approach, I mean, these cues are anyway here in the microphone, so why don't you estimate the signals in these microphones? So, what does this method do? It starts with an assumption. It really assumes that the noise components in the external microphones and the head-mounted microphones are uncorrelated. So, what does this mean? Let me first explain and then explain also different scenarios. So, that's actually quite okay when the distance between the external microphone and the head-mounted microphones is large enough and you have some diffuse noise field. What is large enough? Actually 20 to 30 centimeters. It's more enough for this assumption to hold pretty well. So the external microphone should not be somewhere on the head. If it's on the same body or just lying on the table, that's typically far enough. Diffuse noise field, I will still comment actually on it in later on when I'll talk about the simulation results. So what happens then if this assumption is satisfied? If you look at this covariance matrix of the noisy signal and you look at the column or the row corresponding to the external microphone, basically here the assumption is that there is no influence of the noise. So this just actually contains speech information. So basically this is actually an estimate of your relative transfer function of the speech, of the desired speaker. So basically you can just use all of the, let's say, the noisy correlation matrix, compute, let's say, take the correct column to estimate the relative transfer function, normalize by the correct element, and you have an estimate of your relative transfer function vector.
And then you can do beamforming.
And then you do beamforming with all the microphones, without knowing where all these microphones are. It's completely blind. The only thing is there's one element which is biased here in the external microphone itself. You can compensate for it. At least we also showed it's just a real valued bias, so it doesn't compensate in the beamforming the phase difference. So the phase is still correct. It's only a real valued bias. Yeah, just as a note. So typically we don't even, compensate for this bias, but you could do it. So this is very low computational complexity, and as you will see in the next slide, it has a similar, sometimes in practice even better, performance than this state-of-the-art covariance widening method, which needs an eigenvalue decomposition in each time frequency. So this was a simulation setup with one external microphone in our lab. We have again this binaural hearing aid setup. There is one external microphone. I should have a look where it is. Here it was a bit further from this microphone, so it's like 1 meter. And we have a moving loudspeaker. So really moving loudspeaker, somebody physically moving the loudspeaker, such that we have also the reference signal available in the which we want to estimate. What are the results there? Let me guide you through this picture. So this is the SNR improvement over time. And first, for example, let's look what happens to the external microphone, EM, so the green line. Of course, if the loudspeaker is close to this external microphone, very high SNR. If it moves further, lower SNR, but still quite high.
Increases.
Logical, just to show people, it matches with what you expect. Then let's look at what happens if we only filter these microphones. So local microphones, where, let's say, the typical scheme in hearing aids is that it's just fixed and it just steers towards the front. assuming that people don't move their heads. Of course, then you get some SNR improvement if the source is also coming from the front. However, when it moves away, then you even get negative. Also logical. If we then track where the source is, we get a better and a little bit more constant performance when just filtering, so with the dashed line, the hearing aid microphone signals. What happens now if you filter all the microphone signals? We get these dashed blue and red lines. And what you can see is that the SNR improvement is first of all larger than the external microphone. You might now say, well, it's not a lot. We agree, it's not a lot, but it's larger. And secondly, and that's even more important, I would say, you also preserve the binaural cues of this target speaker. Because if you would just stream the external microphone to both sides, you really get like in-head localization. No cues at all, actually. So it has, let's say, two advantages, both more noise reduction as well as preservation of the cues of the target source. What we also did, but I will skip this just for time reasons, if you have multiple external microphones, basically each of these external microphones can generate an estimate of the same RTF vector. And if there's no estimation errors, you live in a perfect world, it is the same estimate, so you don't need it. In practice, of course, there are estimation errors. And so what we did in the WASPA paper last week, that was presented last week, is combine these estimates. And it can be combined in different ways, either based on input SNR or output SNR. Of course, this was better, but a bit more complex. And the nice thing is you don't have to estimate these SNRs very accurately. You can just use the noisy covariance matrices, because basically what you just want to do is decide from which of the microphones to use the estimate. So you don't need an accurate estimate, you just need to know in which microphone was the highest SNR.
Do you assume that the sampling rates are locked?
Yes.
Yikes!
For now we do. Yeah. I mentioned in the beginning. Yeah. So it's an important aspect. But I would say, at least to some people I talk to, they say it's almost a solved problem. Industry should solve it. You guys should solve it, or have solved it. Yeah. So for now we assume this. That's and also the students working on this. Actually, in the next week, that's exactly what we will do to also figure out how important this is actually, and what happens if we have some compensation schemes for.
Technically, you track the relative
transfer functions. Yes.
So if it is the drift is enough low, you should be able to.
Yes, exactly. Because that's the nice thing about these relative transfer functions. Whatever is there, it will estimate the relative differences. If it's due to movements of the head, movement of the speaker, also a slow movement of the sampling rate. But I'm not sure what.
Several minutes, yes, but in 1 hour they can be shifted quite substantially. Then you should basically take some.
Yeah, exactly. There will be some times when it really shifts a lot, and then when it moves outside of the frame. So everything has to be, of course, correlated in a frame. Otherwise, you have a problem. Yeah. So I cannot really comment on it, because that's something we, of course, realize that we have to check. This question always comes. Yeah. So we really also want to check what happens. So in the demo, you will see actually just a video. There we had It's a perfect scenario, but we also have other demos there. Somebody wearing the external microphone, so it's a very high quality. It's also an analog transmission to the same sound cards, so we can still freely move around with it. Some pseudo-diffuse babble noise. So let's see what happens here.
So first, let's listen to the unprocessed hearing device input signals, where we not apply any noise reduction, but where the spatial perception is correct. That means you're localizing me correctly now on the right side. You're able to follow my movement by listening to my voice, and you're now localizing me correctly on the left side. The overall goal now is to reduce the undesired background noise while preserving the spatial impression of HSDC. In a system where we not only have access to the head-mounted microphones of the hearing devices, but also to an external or remote microphone that is attached to the shirt of the speaker, for example, one idea is to just stream the external microphone signal to the hearing devices and play it back. By doing so, as you can see, we can acquire a much higher signal-to-noise ratio, but the spatial perception is completely gone. You're not able to follow my movement anymore by listening to my voice, and you're not able to localize me correctly on the left side now. To counter this problem, we are now combining the external microphone with the head-mounted microphones and process all microphone signals together in a binaural noise reduction microphone. As you can hear, by doing so, we apply a significant amount of noise reduction to the microphone signals and preserve the spatial impression of the acoustic scene. That means right now you're localizing me correctly on the left side. You're again able to follow my movement by listening to my voice, and are now correctly localizing me on the right side. For you to get an impression of how fast this algorithm is able to adapt to new speaker positions, I will now remain quiet and go back to the left side. And as you can hear, the algorithm is able to adapt to new speaker positions very quickly. But how does this work? What are we doing here? We are using a...
That's what I explained. So a couple of comments here. A couple of comments, because, of course, perfect position here. I mean, that's very high SNR. So what we also had is just external microphones located in the room, especially if you have multiple ones, and then it will either select the best microphone, not the best microphone, but select that one to estimate the RTF, yeah, or combine all of them. Second comment is, this was for diffuse noise. So comment what happens with multiple speakers. So once this demo was in place, real time, then you can do a lot of experiments. My first question was, okay, what happens now when we have multiple speakers? I didn't know what would happen. And what actually happens is, if the speakers, both of them are very coherent, that actually both are preserved. Because basically it will estimate, assuming a bit of sparsity in the time frequency domain, in a very fast way, the RTF of one speaker and then the next speaker, and just switch actually between both. And you could say, well, in some scenarios, that's actually not really undesired. If you're having a conversation with two people, two persons, well, maybe you want to just keep both and let the auditory system itself figure out to whom to listen. If somebody is moving further away, so it's becoming more like incoherent source, then it's being reduced. So it was never designed, let's say, having this as a goal, but that's basically the analogy of the algorithm, what happens if you have also multiple coherent speakers. Okay, that's basically what I wanted to talk about. Well, okay, current future work, of course here, synchronization and also latency issues. I mean, although it should be realized we don't have to know how far the external microphone is away, it's all blind. That's what something I mentioned. We're doing more like analysis of what happens for different coherent speakers. And then, of course, much more complex scenarios where, of course, we have more moving sources and where we aim at integrating, let's say, more some computational auditory scene analysis. So in this talk, what I talked about is speech communication applications. Latency is important there, so that's why we have to go for online algorithms. Also, dynamic acoustic scenarios have to be treated with moving sources, so batch algorithms are not an option here. I talked a bit about joint noise reduction and dereverberation algorithms, two classes, very classical beamforming as post-filtering, where we now have some techniques for estimating all of the spatial and spectral variables together in a joint way, and also doing reverberation suppression using, for example, multi-channel linear prediction or weighted prediction error methods. And then in the second part, I talked about binaural hearing devices, where the aim is not only to reduce noise and reverberation, but also to preserve the acoustical impression of the scene, where I talked a bit about easy extensions of binaural NVDR and multi-channel Wiener filter by just mixing the signals, and there are different mixing factors, and also an improved performance when additional external microphones are available. Of course, I didn't do this work all on my own, but there's many people involved over the years, and also some funding agencies, and we'll be happy if time permits to still take some questions and have discussion. Thanks.
What is this? Guys, we have to finish. Yes.
Very good.
We'll ask questions at least, yes, during lunch, and I will...
Very good.
At 1, I will join you guys for the demo set.
Perfect.
Sorry for the rest.
No. Everything fine.